Imagine stepping outside beneath a full moon at midnight. Suddenly, its silver disk vanishes without a sound. Reflected light continues for 1.3 seconds. Then, stars replace the moon's familiar bright circle. The ground stays still, while your feet remain planted. Earth keeps circling the sun, and breakfast still happens. So what changes first, once the obvious panic fades? Start with the force already moving every coastline tonight. The moon pulls unevenly across Earth, raising two broad tidal bulges. When that pull disappears, ocean water cannot freeze in place. Existing waves and currents keep moving while the oceans readjust. Coastlines would see confused tides before new patterns settle down. The sun still raises tides, with under half the moon's force. So tides continue, while each coastline develops a different range. Ocean depth, bay shape, and seafloor geometry control local height. Many ports would record smaller tidal ranges and weaker currents. Some resonant bays could respond oddly, defeating any universal percentage. The familiar spring-neap cycle disappears because lunar alignment no longer exists. Tide charts become obsolete within hours. Ships and ferries need new models. Storm surges still happen, driven by wind, pressure, and solar tides. Now shrink the twice-daily flood across mudflats and reefs. Barnacles, mussels, crabs, and seaweed occupy precise tidal bands. Their feeding, drying, and predator exposure schedules suddenly shift. Estuaries receive weaker flushing, changing sediment and salt patterns. Tidal power turbines lose much of their predictable moving water. Ecological disruption begins along densely occupied ocean edges first. Back on land, darkness changes before the tides reveal missing gravity. Full moonlight reaches roughly 0.3 lux under a clear sky. Cities barely notice, since streetlights overwhelm that faint natural glow. Remote forests, deserts, and oceans lose their strongest natural nighttime light. For nocturnal animals, brightness often controls when hunting feels safe. A 2023 Australian study tracked 7 small mammal species with cameras. Their activity fell 40 to 70% as moonlight increased. Permanent darkness removes that cue, reshuffling contact between predators and prey. Different species respond differently, so one neat outcome would mislead. African dung beetles can navigate using polarized patterns in moonlit skies. Remove that signal and straight escapes from food become harder. Corals also synchronize reproduction using temperature, sunset, and lunar timing. Experiments show moonlight and post-sunset darkness can shift spawning nights. Existing biological rhythms would initially continue after the signal disappears. Species tied tightly to moonlight face the greatest pressure to adapt. Meanwhile, today's ecosystems absorb missed meals, mismatched births, and altered migrations. Astronomers lose lunar eclipses, while solar eclipses vanish entirely. The month survives on calendars, detached from visible phases. Lunar spacecraft lose lunar gravity and enter new trajectories. Lunar surface equipment becomes debris on new trajectories. One popular claim predicts Earth immediately tumbling or leaving the sun. Neither event follows. Earth's solar speed stays near 30 kilometers per second. Earth and Moon once circled a shared center inside Earth. That monthly wobble moved Earth at roughly 12 meters per second. Removing the Moon leaves a tiny correction beside Earth's solar velocity. The planet continues around the Sun on a slightly changed orbit. Part's spin also keeps its present speed through the morning. Today, lunar-driven tidal friction helps lengthen the day over centuries. Without lunar tides, solar tides still break rotation more weakly. A 24-hour day therefore survives, while its long trend changes. The deepest effect needs millions of years to unfold fully. Earth's axis tilts 23.4 degrees relative to its orbital plane. The Moon's torque helps keep that tilt within a narrow range. In 1993, Laskar, Jutel, and Robutel modeled Earth's missing moon. Their model expanded Earth's chaotic tilt range from 0 to 85 degrees. That range describes possible dynamics without predicting a rapid flip. For many millennia, human observers might measure only subtle drift. Across geological time, seasonal sunlight patterns could reach unfamiliar latitudes. Higher tilt can give polar regions stronger summers and darker winters. Ice sheets, deserts, forests, and ocean circulation would repeatedly relocate. A larger tilt increases seasonal contrast, especially far from the equator. Rapid climate swings could erase habitats faster than specialists adapt. You survive sunrise, yet every tide table becomes wrong. The empty sky becomes the least complicated consequence.